So let me open up Visual Studio and we'll do some examples with, we'll start with, we'll kind of add exceptions into here. Well, let's do some simple exceptions and then we'll do some STL structures and then we'll get into the templates. So we'll keep this one kind of simple. And just look at how exceptions can be used basically for a single function, because usually when you throw an exception, it will be something inside of one function. And then when you're calling it, you'll be listening for that error to pop up. So if you haven't seen this already, this is the C++ documentation website. There is the std except, or the standard except library of exceptions that they provide for you. You can also build your own, but we don't really need to. And there's different categories of different kinds of exceptions. So for instance, maybe I have a function where it could have a logic error, or it could have an out of range error. It could have different types of errors that occur. You can throw different kinds of errors and you can catch different kinds of errors and handle them differently, which is why exceptions are a really powerful way to write robust software where, you know, if it does this error, we fix it this way, then we come back to the program and everything should be good, or like the data shouldn't be corrupted. Those are some of the kind of safety guarantees that we would make. We're not going to get into really deep design with this right now, but you'll see exceptions as we work through other data structures. So for instance, let's say we're just doing a very simple division function. We'll do float numerator and float denominator. And if we had no error checking at all, it would just be numerator divided by denominator. Oops. And let's go ahead and just ask the user to enter those values. And then we get a result, or the quotient, and display it to the screen. So a pretty simple function, but I am able to pass in data that is going to cause the program to crash. So if I run this and give it some numerator, oops, and a 0 for a denominator, well, in some compilers it might crash, but in this case it just says infinity. We don't really want that as a result in our program. That will kind of give us like undefined behavior of like, what does our program do with infinity as a result? So generally, we'd want to have some sort of error checking. So we could say if denominator is 0, then this is an error. You could display an error message. And again, we're not using exceptions yet. Let's just think about if we didn't have exceptions as something available. If I try to build this, it should give me a build error because this function, okay, it didn't build, but should have a warning at least, that this function should return a value. Oh wait, it is returning a value. It's just giving me an error before it says infinity. But if I did this as an if-else statement, then it would complain. Okay. So in this case, it gives me a warning. If we have division by 0, it just displays a error message and does not return anything from the function. But since this has a float return type, it needs to return something. And so it's complaining Some compilers won't let this build at all, but in this case, it's letting us build, but not everything returns something. So now what happens if I try to give a 0 denominator? It says error cannot divide by 0, and it gives us a quotient of 0, but we can't rely on that being 0. Technically, it's just going to grab some random data from memory or something like infinity. It's doing something weird because we're not returning any data. So basically, let's say again, we don't have exceptions yet for an error. If we had divide by 0, maybe we could return 0 as the default value. But then the problem is we're receiving a number as a quotient. How do I know that this is a valid calculation or the kind of default error value? Because if I did 0 divided by 5, that would just give us 0. And so this quotient is fine. But if I did 5 divided by 0, it would still give us 0 and it would display an error to the screen. But there's no way I can say, is this 0 valid? So that's where exceptions come in, where we can literally have a program saying something didn't go right. This other part of the program, hey, the function call failed, handle it in whatever way you decide is best. And then you don't have this sort of like, what is the error default value? Is it valid, blah, blah. So in this case, instead of returning 0, we're going to throw, and we can look at the family of different exceptions. We could say invalid argument, just to say like, 0 is not valid as a denominator. So throw an invalid argument type. And a nice thing about exceptions is we can add a error message using the constructor here. So instead of doing a cout, we can put it in there, get rid of that. And then now we have an exception object. It has a type of error that it is, and it has an error message. So then we can also use that in multiple ways. We can print it out to a log, we can display it to the screen, anything else. So at the moment, I am throwing an exception, but I'm not catching it anywhere. So again, if I do 5 divided by 0, it's going to do this. And you've probably seen this sort of thing happen before, maybe not in this context, but using something from the standard library, and then it crashes and it says exception unhandled. So then you need to kind of look at, well, okay, what does this mean? In this case, the exception is unhandled because we threw an exception. We're saying there's an error, but we're not listening for that error and we're not handling it, basically. So in order to do that, we have our throw here, but down here where we are calling the function that could cause errors, we need to surround it with try and catch, which I'll fill in a moment. And so tries to call the function that is a risky function, catch. It should be catching the same data type as whatever the argument is being thrown. So we'll say catch invalid argument EX. And we'll just throw this part in here too. You could also sometimes see this as a const reference to an exception type. Same sort of thing. It's just a little bit more memory efficient to make it a reference than to have a copy. So if we do that, that's a copy. If we do that, we have the exact exception. We have direct access to it, but we can't modify it. So in this case, when we catch the exception, now we have to decide what do we want to do if this kind of error occurs. So we could continue running the program. We could just say like cancel the current operation, but continue the program. We could tell it to close the program. So for instance, if the function failed and this was like a big program and we couldn't be sure that the data was still valid or like good, not corrupted, then maybe we would want the program to close and reset. Or sometimes we can just kind of like see the error maybe log it, but then not do anything about it. Sometimes you don't really need to deal with the error to make sure everything in the programs will kind of just keep going. So it's all just a design decision. And I know we have like a really simple, small thing right now, but if you were working on something bigger, you would want to have a decision on how that works. So in this case, we can do cout again and say ex.what, which the .what is a function that will return our error message here. And hi, John, did you have a question? Okay. And in this case, we have our error message displayed, and let's just say we can't continue the program. So then we can run an error code if we wanted to. So if we build and run, enter a numerator and a denominator, now it says cannot divide by 0, and then the program closes. It exited with code 1. You know, or we could do something else, like maybe if we wanted the quotient to be the default value, we could set it there. But this is just a very, very stripped down example of writing an exception to handle some sort of invalid state. Another example of what could be an invalid state, let's say we absolutely need to load some data from a file. Let's just pass in a file name. And I'm going to include fstream. So in this case, let's go to the folder where the project is. I'll make a little data file. And I don't know, let's just say it's 100. And maybe that's a bank balance or something. So we have a file name. We're going to try to read it in. So input file stream, input, pass in the file name. So this is creating a file input stream so we can read from the file. We can do if input.fail. Well, we could display an error message, but also then what do? This is failing. We can't load the file. So does the program crash? Do we need to load a default? Anything else like that? So in this case, we could throw, let's look at the exceptions again. Let's just say runtime error. Cannot find file. You can append the file name just so it's more clear. So if it fails, we'll throw an error. Otherwise, say float balance, we'll load in the balance from the input. And let's just return the balance as well. So I'm going to change this to a float return type. So if we end up running and hitting the throw command, it won't finish the rest of the function. That's also another nice thing about our exceptions, is that it will not expect us to return data, even though it has a float return type or a float return type here. Once it hits the exception, it's going to go to the catch and execute there. We do not have to having a float return value when we have a throw. So we have load data. We'll just add something down here. Float balance is equal to load data. We'll pass in, so the proper file name is data.txt, or we could ask the user to enter it. And I think this is going to fail to build because I'm not including the string library yet. Okay, it's not. Sometimes it fails whenever you don't include string. So we do that, but again, the load data is a risky function, so we'll wrap it with a try and a catch. We'll try to catch runtime error. And if that occurs, we'll say ex.what, and we'll return another error code. Otherwise, if we're done over here, this is the clear balance ahead of time, so we can use it outside of that scope. We'll say current balance is, and then we'll display it to the screen. So we'll go ahead and build and run. Let's do that. For the file name, we'll do data.txt. That's a valid one. It finds the file, it loads it in. If we run this again, but we give it a file name that it does not find, so let's say bank.txt, it's going to throw the exception. It'll give us the error message, cannot find file bank.txt, and then the program closes with the code 2. So again, if this was like a larger program, you could say the file was not found, enter something else, try it again with a different file name. But in this really, really simple example, we're just kind of having the program crash, or not crash, but like close when we don't have the right data we need. Any questions about exceptions at this point? I'll upload this example code to GitLab. I just have to log in. So there is an example code repository. Let me make sure it's linked to up top. We have the quick reference. Add the link to the example code repo. Oops, nope. So if you go to the example code repository, it kind of has example code for CS200 through some 250. But I'll just throw it in here. Well, I'm going to put it as 235 because we covered the same topic in there, but we'll do new directory, CS235. Actually, I have an exceptions one already. So we'll do CS for fall 2022, simple exceptions. And so this will be in here. I'll, in a little bit, put the links on the Canvas page. Okay. So that will be up here if you need to reference that again later. So for now, I'm just going to erase all of this and we'll keep going. Okay. All right. So let's also talk about the STL library. So in C++, there's a lot of library functionality and objects, classes that are part of the standard library. Not everything is included all at once, because if you just included the entire library of everything, that would make your executable file really big. So you kind of just include the certain things that you want at a time. So if I change search for vector, vector is a data type. If you recall, we used arrays kind of as the first data type, or a data structure where we store a bunch of data of like types in it. There's issues with arrays. If you do just your normal traditional array, it's fixed at a certain size. You can't resize it. If you remember using pointers to make dynamic arrays, you can resize it, but it's kind of a pain in the butt. And you also have to make sure you don't go outside of bounds of the valid indices. And so it's all kind of just this, a lot of extra code you end up having to write just to manage some data. So a data structure is where you write a class, you put that array or that pointer inside of the class, and you build out functionality that will handle adding, removing, accessing items. It'll handle detecting errors. It kind of gives you a nice little interface where the user or the other programmers just see, yeah, I can store data, I can add it, I can remove it, I can access it. But they don't have to worry about freeing memory resizing and allocating new memory, going outside of bounds. They just kind of assume that there are error checks for that and everything is good. So for part of the exercise for this week, we're working on our own myVector class, but we're going to start off with just vector here, which is part of the C++ standard template library. So a vector, technically, it is a dynamic array. That's how it works behind the scenes, but we don't really care. We don't need to know that. We just care that it contains functionality that is useful to us, like what is the size of the array, or basically how many items are stored in it. Is the array or the vector empty? Get an item at position 0 or 1 or 2. Add a new item to the vector, remove an item from the vector, insert an item somewhere like in between other elements, erase an item, clear the entire vector, and so on. So it gives us this nice little interface. So over here, let's just start off really simple again. And we'll have a vector strings. I also need to include vector up here. This will just be called, let's have course codes. And we can then add new things to our course codes vector object with its pushback function. And if you click on any of these links, it'll give you some example code as well. So for pushback, we pass in some value. It'll add it to the array. We don't have to worry about how it does that or where it puts it. It just adds it in there. So we're going to do push back, and I'll just hard code CS134, CS200, and so on. So then that adds 4 items to our vector. We can then access those items. So we could say item number 0 is course codes at position 0. I'll just run this as it is at the moment. Item number 0 is CS134. We can do a for loop. So we can do for size ti for index is 0. I is less than the course code's size. So how many items are in there? I++. Item number I is course codes at position I. I can erase this guy up here. That will display everything to the screen. This is just our normal for loop. And then as of C++ 11, like 2011, we have range-based for loops. So we could say for auto element in course codes, output the element. So in this case, this gives us these here. It'll iterate through every item in our vector or array or whatever we're using, store it in a variable called element. So we just get the value, not the index number, and we can display it to the screen. So that's an option if you don't need the index. Usually I tend to need the index for different things, but that's there if you need it. If we wanted to, we can also remove stuff, but we'll just keep going with this. So we have a vector of strings. I'm going to make a simple struct, such as a course, and we'll give it a code and a title. And we can add more information if we wanted to, but we'll just keep it to like the CS200 concepts of programming with C++. So now instead of having a vector of strings, which is just the course codes here, I'm going to create a vector of courses. I'll just name it courses. We can get rid of this part as well. Now, I can't just say courses dot push back a code and title. It won't let me do that because it is supposed to store a course, not 2 strings. These are just 2 strings on their own. I could create a little constructor, so we'll just have a default constructor that does nothing, and one with a code and title that initializes it for us. So we'll say code is C, title is T. So then if we put this in a course constructor, that basically creates a new course and then also passes it to the vector at the same time. So we could do that. CS250. So this was programming fundamentals, concepts of programming, object-oriented programming, and data structures. Okay, so we have our course object. We could also technically create a course and set it up. Course.code is CS210, course.title is discrete math 1, and then we could push that in there as well, courses.push back. So here, this is the course, courses is the vector. If you wanted to, you could pre-declare the object variable and then add it into the vector. But if you don't have to, if you can just do it through a constructor and you don't need to initialize the data before passing it in like that, then that's usually a lot cleaner. Okay, so we have our vector of courses. We can use the same for loop style to access each item. But now we can't just access, it's called courses, but we can't access item I because it is a course object. It does not know how to display course I because we haven't told it how to work with the cout statement, which that's something we do in CS235. We don't generally hit on that in CS250, but you can basically implement the cout operator or the output stream operator to basically say, this is how you cout a course. We're not going to worry about that. So down here, instead, I'm going to say course code and courses sub I dot title. So it'll just output the data that belongs to it. So we can run, and it gives us that data back. Let's go ahead and add one more item. We'll do credit hours, which I think they're all 4 credit hours, except maybe 134. So we'll just add int that. Now, I don't really like these variable names. Usually I do the whole prefixing these with m underscore, so I don't have name conflict. We could also make this, for example, code, but then we'd have to say this code is equal to code, where this arrow code is this, and that one is this. It's kind of hard to even like verbally say that. It gets everything kind of mixed up. So I'm just keeping them as simple variable names right now. We have credit hours. We can then add these in here. Oh, this happens every time. No one's moving, so it turns off the lights. Yeah, I usually have to like walk over here to even get it to turn back on. A good design for a computer class where everyone's going to be sitting at a computer doing nothing. Okay, so we have those. We can also display them. So let's say courses I dot credit hours. And we'll add that in. Go ahead and build and run. Now we have all that data. But now what I'm going to do is I'm going to replace this vector with a map. So currently, each of these elements has an index 0, 1, 2, 3. those don't really mean anything. It's just the order in which they were added to the array. But with a map, we can give its index or its key some sort of significance. So if we include map here, are you mad? That's okay, I don't care. We can change this into a map instead. And a map is kind of similar to a vector, where it still stores a series of data, but instead of an integer index 0, 1, 2, 3, 4, 5, we can literally have anything as the unique identifier and then still point it to some course. So in this case, I'm going to use a string as the key and course as the actual data. And I'll go ahead and comment these out. So in this case, the key would be a string, and I can use something like the course code as the unique identifier, because each course should only have one course code. So courses, and then I can literally just say CS134 is equal to, and I'll just copy paste this constructor, and then that sets that whole thing up. The course at the key CS134 is specifically this course object. And we can do the same for the other ones. So CS200, CS225, CS250. And just move these. Okay. So we could ask the user enter the key of the course you want more information about. Let's create a string key, have them enter it in. And if it's not an invalid key, we can just display it to the screen. So we could say cout courses at that key dot code, comma, courses at that key dot credit hours, and courses at that key dot title. So now if I run this, I can say CS134 and it gives me that data. But if I give it a invalid key or a key that is not currently stored in there, like CS211, it's going to give me garbage. So whenever you see weird numbers like this, that means it's garbage, it's something random out of memory. It means something's uninitialized. In this case, CS211 is not added, it doesn't exist, so it just gives us garbage. But we can check to make sure that we're not going to get garbage. Let's just go over here and look at the map library. And there's a few different ways. We can use the @ function instead. Let's open those two up. And then there should also be a find. So I don't think we're using find in the exercise, but I'll show you these two. So @ and the subscript operator do the same thing, except, let's see, where's the, down here under exception safety, it says if the exception occurs, there's no changes to the container. I guess we'll try the try catch on it. I think that with an older version, the subscript operator, the square brackets, did not throw exceptions, but maybe it does now. So we'll just try that. Try catch, and it should tell us what kind of exception it would throw. Okay, so if @ throws an exception, it's an out of range error. And if, I don't think this one throws an exception. I'm not really sure how I'm supposed to read this. It does add a new item, but as far as accessing that item, it does whatever. Okay, so we're just going to change these to, instead of courses at subscript key, we'll use that at function instead. So they do the same thing, except at will throw an exception if it can't find that key. We need to catch a runtime, no, out of range error. And again, this could literally be written this way. It's just that copying, creating a copy of data is a little bit slower than getting the reference of it. Our exceptions are pretty small, so it's not going to be a big difference. But we'll talk more about algorithm efficiency later in this course. So in this case, we'll display an error. ex.what should give us the error message. So inside of map, it has that exception thrown. We don't know what the error message is because we did not implement it. But we'll go ahead and try this out. Course key, CS211, invalid map KT key. Well, that's not very descriptive, but at least it gives us that exception. Now, if we had an exception that we were listening for, like a logic error, and we weren't listening for this one here, what happens if the function throws an exception, but we're not listening for that kind of exception? Well, if we build and run, okay, it's not supposed to do that. I don't know why I did that. Okay, let's do it this way, where we'll see if we just don't have the try catch around it. Then when we don't handle that exception that gets thrown, it again gives us the exception unhandled error. And so if you're running Visual Studio in debug mode, it just crashes to a location. Now, I know that this C++ code is really weird looking because it's part of the standard library. It's probably been optimized in various ways, but you can at least kind of see what's happening. It says mapped type. So we're working with a map. It has some sort of mapped type thing declared. It's the at function. We have a key type and a key value. So it's throwing an exception in here. And so that should tell you that our maps at function is throwing an exception. So don't just kind of glaze over the weird code. You can still glean some information out of it. Also, if you have your call stack open, you can double click on that and see where the call failed. Okay, so we keep those in there. I assumed, I don't know why it didn't do the same exception thing. Every compiler is different, I suppose. And I mostly use the G++ compiler. I'm in Linux most of the time. So I have no idea what Microsoft does with their free time. So, okay. Any questions about the vector or map data types? Yeah, so someone in chat mentioned that maps are like dictionaries in Python. That's exactly what they are. And as we get further into the class, we'll learn about another name it has is hash table, because if you're familiar with like a validation hash when you're downloading a file, I don't know if people even usually do that anymore, but hashing is taking it and giving you some kind of unique thing out of it. When you encrypt certain data, or like it'll hash your password and then you can't read like a plain text password, blah, blah, blah. Hashing is just the process of taking some input and giving you a unique output. But the hash table, aka dictionaries, is something we'll implement at the very end of the class. So just like in Python, or if you've looked at JSON files, or worked with something else that has key value pair associative arrays, those are all the same thing. Okay. Finally, let's look at the template, not template, we'll work with templates, but we're going to just start off with the myVector class and use that as the template example. So in the exercise for program 5, we'll implement this myVector class, and then you'll also use it in program 6. But basically, the data structures class is all about writing our own data structures. So this is going to be a dynamic array. We'll just kind of step through implementing it, and then it can be used in other places. So I am going to create a header file. Call this myvector.h. I don't want pragma once. I'm going to do if not defined, my vector, define my vector, and if. Technically, the pragma once does the same thing, but it is not universal across every C++ compiler, so it is better to just use the if not defined method. Again, pragma once I think is a Microsoft thing, so it's just they add stuff sometimes that is only for Microsoft's compiler and doesn't work for a compiler in Linux or Mac. You have to deal with it, so that's why if you end up using something that's not cross-platform in your code, I'll usually leave a comment of like, hey, don't use this. I don't usually take off points unless you keep doing it over and over, but okay. So we're going to create a templated class for the vector. And when we are writing a template, we need to make sure our function definitions are also in the header. So this is kind of the reverse of what we tell you when you're writing just a normal class or a normal function, where your function declaration is supposed to go in the header and your function definition is supposed to go in a CPP file. You're not supposed to do that with a template. So let's just start this off and I'll explain it a little bit more. So with our template, we're specifying a placeholder type name T. So if we have integers or floats or strings, those can be inserted into that T. We don't know what it's going to be currently, but we want to write our vector to allow for any data type. Why would you write a data type that, or a data structure that only stores strings or only stores floats? Generally, you want a structure that stores any kind of data. So we'll say class my vector, open close curly braces. And so now we can store T as a data type somewhere in this thing. I'm getting a UMKC donation call. We're going to skip that. Okay. So we'll do public and private. And for if we were doing a dynamic array of, for instance, floats, we'd have float m array. And then to initialize it, we do m array is a new array of floats of size whatever. But we're going to use T instead, because we're having a placeholder data type that's going to be a dynamic array of some data type. And so when we initialize it, it will be T. So anytime you see float or int or whatever for whatever you're storing, you're going to replace it with T. Now, in some C++ examples, you might see just capital type. I like to use T just because it's very obviously, this is a template. This is not a constant, named constant. It's not a different defined thing. T is pretty much what templates use or as their name. So we'll create our array. I'll just slide this over here. I don't know why this resolution is so small. We have the array. We're going to have the m array size. So we need to keep track of how big do we make our array to make sure we don't go out of bounds. And then item count is going to be, okay, our array is this size, but maybe we only stored 1 or 2 pieces of data in it. So we have the array size, we have a bunch of blank spaces, and then as we add stuff, we add on to the item count. And up here, we'll have my vector constructor, my vector destructor, void pushback. So just like how the vector I showed you on the documentation page has a pushback function, wherever that was, go back to vector. We're going to implement our own. So there's pushback. And pushback is going to need some sort of data, which is the new item we're going to add to our array. Since our array is a T type, this needs to be T data. So we'll just say item. We might want to retrieve the item at some index. So we'll say return the T type, get at, and we'll pass in an index. We might also want to know how big the array is or how many items are being stored. So we'll say get size. We might need to resize the array if we run out of spaces or blocks. So we'll say void resize, size T, new size. Now, technically, this is marked as a public function, but I would actually make this a private function, because if other programmers are using your vector, why would they need to manually hit the resize? That should be taken care of automatically. So I'm going to make it private here. We also have a private allocate memory, passing in a size for it to be, and deallocate memory. And bool is full. Now, I'm making the is full function empty also because to the user, yeah, okay, just a minute, I'll answer that in a second. Is full is currently private because if this is a dynamic array, the user or the other programmers don't care that if it's full, because if it's full, it just resizes and then it's not full anymore. So this is just kind of like a utility function that we'll use. So the private members here, you can also use an integer. Size T is just another name for an unsigned long, or you could do unsigned int, since technically a size won't be a negative value. Usually you'll see size T specifically when it relates to a size of something. This could be an instance instead. So you can use whichever of those. You'll just get warnings if you're doing like the for loop with the STL vector and trying to get its size, because that's going to be a size T. And if you try to compare a size T to an integer with greater than less than, then it's going to throw a warning because they're different data types technically. Okay, so here's our vector template. And now we need to create the class, the function definitions, and those need to go inside of this same.h file. We do that because technically this is not C++ code. It looks like C++ code, but what this is it's a literal template where the compiler is going to look at this and it's going to look at where we're using it. So for instance, let's kind of add this over here. We're eventually going to use a vector, my vector of courses. So when at compile time, what it's going to do is it's going to say, okay, we're using a my vector of courses. Maybe we have something else of maybe campuses. We have a my vector of strings. Those are the two data types we're using with this data structure. So what the compiler does is it copies this, and then it basically will create a copy and make the version that has the string, and it changes all of the T's into strings. And then it makes another version for the course version, and then it makes a bunch of those. Compiler is technically writing some code for us, but from our side, it looks like we're writing just kind of normal C++ code. So that is why everything has to be in the header file here. So if I copy these functions, we'll need to create definitions, but they all need to be in the H file. So then the definitions will look like it's going to be a my vector of type T, colon. Now it's going to say, what is T? Well, we need to put the template type name T in each of those spots. So then all of the function definitions will look like this. And we need a function body as well. So I'll just copy and paste this here. Okay, so then we can implement these. And then this kind of steps through what the different functions will do. So let me see if we have a split option. Yeah, I'm going to keep these split so we can reference the class as well as working on the functions. And we'll put this over here. So we'll just go in the same order as what the documentation has. So with the get size, which I guess this is a typo, should say get size. Down here, it should return whatever the item count is storing. So again, even if the array has 10 spaces, but we haven't used pushback at all, we're storing 0 items. Or if we use pushback a couple times, we're storing 2 items. So the item count corresponds to how many things we've put in there, not the array size. So in this case, we'll just say return m item count is full. Down here, if the amount of items we stored in the array is the same amount as the size of the array, then that means the array is full. So we can return m item count is equal to m array size. It looks like a condition. You could use it for an if statement and return true, return false. But technically, since this returns a true or false on its own, when you're checking the condition, you can just return that condition and it won't give us what we want. Now, I forgot to put the little markers for const and no except in here. Let's go back and do that real quick. So when we mark a function as const, that means the member variables should not change in these functions. So usually it's like a read only. So get size, that one's going to be const. If we mark it as no exception, that means it's not going to throw an exception. It shouldn't do anything that would cause a problem. So get size, again, that's just going to return the size. It's not going to have like a bad calculation or anything like that. So we just do const no except. Get at, that shouldn't change anything, but we could have an exception if we go out of bounds. Pushback, that will change the array. It'll add something to it. So it's not a constant. But we'll mark it as no except because really we shouldn't run into trouble adding something. If our resize fails, that means like the computer's out of memory or something, and that's kind of beyond what we can deal with in our program. Let's see, is full, since that's read only, that's also a const, and no except. Resize, mark as no except. Hopefully we're not running out of memory. Deprecate memory should be fine. If the pointer is null pointer, we'll just ignore it. And then anything else, that's everything. Okay, so now that we have these decorators here, we have to have the same on the function definitions. So it's going to be mad at me for not having those. Okay. Going back here. Get that one's going to be const. With the constructor, we want to always, when we're using pointers inside of a class, we always want to default that pointer to null pointer. Because we don't know what is a garbage address and what is a valid address. So the best we can do is just set it to 0 basically, and say, hey, if this pointer is pointing to 0, that's not a valid address. But if we don't initialize it, it will pull some data from RAM. It'll try to turn that into a memory address. It's basically garbage. And there's no way we can tell if this is a valid memory address or not. We also want to set the array size to 0 and the item count to 0. With the destructor, since we're going to be allocating memory, we want to make sure to deallocate that memory before this object is destroyed. If we don't, while the program is running, that memory is still allocated and we won't have access to that block of data or that memory. So if you've ever seen a memory leak in something like, I guess, older Minecraft, where the longer you run it, like it just gets more bogged down and takes up more RAM, that's what's happening. Like something was allocated and it didn't get freed. And then that just kind of stacks up as it continues allocating memory, and then it becomes unstable. So for here, we'll just call deallocate memory. Okay, let's go and implement allocate memory. So again, these are our member variables that we work with. So its size has been passed in. We want to allocate memory of that size for an array, but we also need to do some error checks. So if our array is currently not pointing to null pointer, that means it's not pointing to 0, it's pointing to some memory address. So we're assuming that's a valid memory address, and we don't want to go then point it to a new memory address, because then this stuff is still allocated, but we are now pointing over there and we've lost track of this thing completely. So if that's the case, we're going to throw a logic error pointer already allocated. If that doesn't trigger, we can kind of keep writing our function below that. So we'll have our array, where we'll initialize the data. It's a new some type, some placeholder type of that size. We'll copy that to the array size, and we'll again set item count to 0 just to be safe, allocating some fresh memory, new array, nothing's in it. In deallocate memory, we need to see if the array is not equal to null pointer. That means, again, it's pointing to a memory address. We're assuming it's a valid memory address. So in that case, we need to deallocate that memory and then reset it to null pointer. So delete the memory at marray, set marray to null pointer, set the array size to 0, set the item count to 0. Okay, with get at, since this is technically an array, an index is passed in, we should be able to return the item at that index, but we also need error checks. So an index is invalid if it's less than 0. 0 is the minimum valid one. Or if the index is equal to the array size or greater than that. So if index is greater than equal to m, I mean, technically this has item count, that would be fine too, because even if it's past the item count but not past the array size, it won't crash the program, but it will give us garbage data, and we don't necessarily want that either. So we'll throw out of range, add index. Otherwise, we'll return whatever is in the array at that position. And then finally with resize, when this happens, we can't technically just resize the array. We actually have to allocate a whole new block of memory of a bigger size, copy everything over, and then we just free the old memory. So we have to create a bigger array. Copy everything over. The new array's item at that position is the same thing as what used to be stored there. Then we free that old memory. Then we update the array pointer to point to the new memory address. Yeah, this video will be posted tomorrow. It should just automatically process and be on Canvas under the Zoom link. So once I close the class for tonight, it should be uploaded and processed up there. Array is equal to new array. Array size is new size. So when we point one pointer to another pointer, it just says that memory address. I am now pointing to the same memory address. So we've allocated a bigger space. Now our array is pointing over there. All right, I think we're almost done. Okay, with pushback, we have a new item. We want to put it in the array somewhere, but we need to do some error checks first, because if the memory hasn't been allocated, we need to allocate the memory. If the array is full, we need to resize the array, and then we can kind of add our stuff in there. So if the array is currently pointing to null pointer, make sure you have 2 equal signs, not 1. Then we'll allocate memory, and we can just do some small size like 5. Else if is full, then we're going to call resize, and let's just pass in the array size plus another 5. So if either of those happen, that kind of gets it all ready for us to then add stuff to the array. Array at item count is equal to the new item, and we'll add one to item count. So starting off, item count is going to be 0 when the thing is empty. When we go to add a new item, it should go to item position 0. Then item count will be 1, and when we go to add the next item, it should be at position 1. So the item count increments, and so on and so forth. So technically, item count can also be used as the next valid index to put our new item. Okay, so in program 5, you'll use the myVector, but we're just going to use it for this example. So in main.cpp, again, we had a vector of courses. So let's just kind of copy this and then reuse it. So instead of the STL vector, I'm going to use myVector. The function names have different casing, so we'll change this to pushback. And instead of size, this is going to be get size. And we can't use the subscript operator. We could implement how that works, but we haven't done that here. So we're going to do dot get at position I. So we're replacing the subscript with our function. Now we can build and run it. And I have a build error, so let's check that out. It says there is a redefinition of pushback. Weird. Also, credit hours is the choice, that doesn't matter. Oh, I also declared courses twice. Different exception specifications. Okay. So what that means is in the declaration for pushback, I said no except. So over here, this needs to have no except. And we'll just double check it for everything. Let it tell us what's wrong. So deallocate memory, it's supposed to have no except. We'll also put that there. Missing curly brace function header. Oh, I put a semicolon at the end there. So a technique for debugging your stuff is fix one error at a time and then rebuild, because sometimes some errors cause multiple issues to happen. Did I copy paste resize too many times? Oh no, different exception specifications. So up here, resize, also no except. So we'll put it there. Okay, now we're good. Go ahead and build and run. It works the same as before. So we've technically just refactored this program. Refactoring means we clean up the code, but change none of the functionality. This is especially frustrating when presenting to your end user, when it's like, it looks exactly the same, but we improved it, I promise. But it's a part of writing software. So that's what we're doing in this class for CS250. We are implementing our own data structures, stuff that stores data, then we're storing data. And we're just basically seeing different ways we can store a bunch of data. That's what this class is entirely about. Any questions on anything we've covered so far? Okay. So I'll go ahead and stop recording. And I'll let you all work on the exercise. So again, this kind of steps through the same stuff we went through with the example code as far as this one has templated functions, which we didn't do on its own, but it'll step through that using the STL vector, STL map, using exceptions, using the template container class, which we just implemented. And then in program 6, you kind of put everything together based on the requirements. So hopefully that will help you out. If you have any questions, let me know. I'll just mute myself and grade things while everyone works and stuff.